Hello everybody, welcome back to our channel. In this episode, we're going to be doing another review session, this time on the topic of thermodynamic cycles for Physics 7A. As usual, if you're finding this content helpful, please make sure to leave a like and subscribe. It really helps our channel. Especially with this new type of review sessions or video, I still don't know if, basically it's worth it, if people are going to be interested in these types of videos. So because I'm still playing around with the idea of going back to 7B and 7C and making more of this, I would really appreciate that if you found these sort of videos helpful. All right, so let's get started. So this is a review session on thermo, and what I wanted was, first of all, I do need to remember this myself, so that's why, if I'm putting in the work, why not make a small video about it? We're basically going to go around the 4 types of cycles that we are going to see on Physics 7A, and, basically how our equations look the same as or different depending on which type of cycle we're doing. So the first thing that you'll notice is that I have my equations over here, because these equations that I have over here, so they are going to be, so these are the general equations, and these equations are going to be useful for every single type of process. So that is why I have them over here. However, they simplify differently depending on the process, and that's where they look different depending whether you're doing isobaric or isothermal or whatever. But the equations themselves, as they are right here, like those are the general ones that you need to be able to start from there, and you yourself need to be able to do what I'm pretty much about to do for you guys here. Now the equations, we have a new equation, which is a work equation, which is the negative of the integral of pressure times a change in volume. And graphically, the magnitude of this work is the area under the curve of a PV graph. So that is always going to be the case. It's always going to be the area under the curve. So whenever you have a cycle or whenever you have a process, then whatever the area is under your process, that's the work. And because of this negative sign, if your volume decreases, so if this is negative times this negative, that makes a positive. And if your volume increases, this is positive, pressure is always positive, so that makes work negative. Now, again, because this is over here at the top, this means that this is always going to be the case. So that's like a rule. Another new equation that we have on Physics 7A, but thankfully a lot of you know it already from like some chemistry classes, is the ideal gas law, which is PV is equal to number of moles times RT. So this is something that we're gonna be using a lot on practice problems, the ideal gas law. Both monatomic and diatomic gases, for the purposes of 7A, we take as ideal. And then we also have some equations that we knew from before, all the way from DL1 actually, but just please note that for the purpose of this topic, I am assuming that whenever we're working with processes or cycles, that there is no phase changes during these processes or cycles, and that is just because it simplifies things, and it also makes it so that we can actually use the ideal gas law. So for the purposes of 7A, every single problem that we're gonna do is basically, well, when it comes to thermodynamics, we're not gonna have a phase change when it comes to these processes and cycles. And because of that, I just went ahead and, already said E bond is going to be equal to 0 for this part of 7A, only for this part of 7A. And because of this, the change in internal energy, which is thermal plus bond, is just thermal if there is no bond. And then from, all the way back to DL1, the change in deltas, which in this case we only have thermal, is equal to heat plus work, Q plus W. Again, this goes all the way back. And the last equation that is going to be useful in this topic is the one that we just learned in the term from our topic of microscopic thermal energy, which is the one that says change in thermal is number of modes, 1/2 kV delta T. So this one is something that it's going to be useful from time to time. So I thought, let's just include it. Okay, so that being said, let's just go ahead and do our processes quickly. The first type of process that we are going to encounter, and I sort of did them from like the least difficult to like the more difficult, is isochoric, or also known as isovolumetric process. Isovolumetric means, iso means no change or same, volumetric is volume. So in this process, the volume stays the same, which means that you have two isotherms, and you go from one isotherm to the other. So you go from, and then it can either be going up or it could be going down, it doesn't matter. But what matters here is that your volume stays the same, isovolumetric, so your delta volume is equal to 0. Now, what simplifies when delta V is equal to 0? The first thing that greatly simplifies is your work. Your work simplifies because work is, so your delta V is equal to 0, and this means that your work is equal to 0. Now, why is this the case? Because work is pressure times change in volume. If your volume isn't changing, then this is 0. So if your volume doesn't change, then your work is equal to 0. So this gets simplified like this. And another thing that simplifies is if this is equal to 0, then we just take it out. Thermal, and then this is just equal to Q because there is no work done. So these are the two simplifications. And then in terms of what is not 0, so your delta P is not equal to 0 because you're going from an initial to final. Delta T is not equal to 0 because you're going from one isotherm to another, so your temperature is either going up or down. Your change in internal energy is not equal to 0 because you still have Q. So just because W is equal to 0, that doesn't mean that Q is not there. And in fact, there needs to be a Q because you do have a change in E thermal. This can't be equal to 0 because there is a change in T, and then these are all constants. So because there is a change in temperature, that means automatically that you have a change in thermal energy, which means that if this is 0, that this also has to exist. So these guys are not 0 for this type of process. Well, then if they are not 0, how would you find them? Well, that's easy. You have to use your equations. So you would use your ideal gas law, so PV and RT. You also use this equation. And then you can also use this equation. KB delta T to solve problems. So say that they ask you for internal energy and you have delta and you have the initial temperature. Well, you can find the final temperature from here, put it over here, then get over here. You know, these are the equations that you would use. All right, so now the second part of the second type of process is called an isobaric process. On an isobaric process, what is kept constant will be the pressure. So you're at a certain pressure, so let's just say this one. And then you have an initial and a final, and then you just move. Oh, that's, there we go. So you have your two states, and then your initial and then your final is the same, like this. Now, in this case, work is not equal to 0. However, work can simplify because work, by definition, is the area under the curve on a PV graph. So isobaric processes, when delta P is equal to 0, are just straight lines, straight horizontal lines, which means that finding the area under the curve is trivial because it's literally finding the area under a rectangle. So finding the area under the rectangle essentially goes your work is just basically the area under the rectangle, which is base times height. So your base is just your delta V, and then your times your height, which is just the pressure. Now let's see. Yeah, actually I don't need, if I put this negative, which comes from this negative, then this is not the absolute value, this is just the actual number. So let's see. So if we go from small to big, then this is positive, the area increased, so this is negative. And we go from big to small, then this is negative times negative positive. Yep, yep. So this is it, this is the simplification. Negative times the area under the curve. So this is the simplification for work like this. And this can either be the initial or final because it's the same, it's trivial to name it. So it's just delta V times P. Now, what else simplifies? Well, not... that's the only thing that simplifies. Delta V is not equal to 0. Delta T is not equal to 0 because you're also going from one isotherm to another one, so not equal to 0. This not being equal to 0 means that E thermal is not equal to 0, which means, and this not being equal to 0 means that this is not equal to 0. And then work is not equal to 0. We already said that. So for all of these guys, if we're doing a practice problem, then our equations that we're going to use is obviously the ideal gas law, our simplified work equation, our internal energy equation, so delta U is equal except now it's Q plus W because work is not cancelled here, is not equal to 0. And then of course to solve problems. So these are the equations that we would use. Now the third type of process that we have It's my favorite, which is the isothermal process. Isothermal means that the change in temperature is equal to 0, which means that basically the entire process happens within the same isotherm. So you can, go up and down. So basically you pick an isotherm, which means that, across the dashed lines, the temperature is the same, and then you move up or down the isotherm itself. That means that delta T is equal to 0. Delta T is not equal to 0 here because you're jumping from one isotherm to another, one isotherm to another, but in this case, isothermal, that means that you stay on the same isotherm. So delta T is equal to 0. In terms of work, your work equation you can't simplify. Sad face. Because the work is still the area under the curve, the negative of the area under the curve. However, it's not as trivial as just multiplying like base times height or something. You actually have to integrate. If you want to get something from this equation, you actually have to integrate because it's not as trivial as just getting like some sort of like square or something. The thing that does simplify is that because delta T is equal to 0, that means that the change in thermal energy is equal to 0 because you will be multiplying times 0 over here. So this is equal to 0. And because if there, again, assuming that there is no change in E bond, no phase changes, that also simplifies the internal energy to being equal to 0, because internal energy is equal to thermal energy. And again, if this is 0, thermal is 0. If thermal is 0, delta U is 0. So I love this simplification. Love it. Now everything else is not equal to 0. So delta B is not equal to 0. You go from initial to final. Delta P is not equal to 0 because again you're going either up or down or whatever. Your Q not equal to 0 necessarily. And then that is also the case for your W. Your W is actually not equal to 0 because you are always going to have some area under the curve. Oh yeah, no, this is necessarily not 0. Necessarily not 0 because if you simplify this to 0, then that means that these two have to be opposite to each other. So the equations that you would end up using is, of course, the ideal gas law. That's always going to be useful. This equation simplifies to Q is equal to negative W because E thermal is equal to 0. And this equation is not really useful because this is equal to 0. So this is not something that you would find useful. And then to solve problems. So you would use your ideal gas law in order to find any volumes or pressures that you're missing on your problem. Then you will be using this equation. And then as a last resource, you can always integrate the work equation. And that's basically how you're going to be solving problems when it comes to isothermal processes. Why am I saying as a last resource? Because there's usually always a way you know, if they give you Q, it's always more clever to just know that this equation holds because delta U is equal to 0 than integrating. But integrating, even though it's a last resource, you know, the beauty of integrating is that because this equation always holds, you know, you're always gonna get an answer no matter what. So that's pretty useful. But because quizzes are usually 20 minutes long and yada yada yada, I usually try to integrate as a last resource. All right, so now the last type of process is my least favorite, and it's the one that I personally find the hardest, and it's called adiabatic. So an adiabatic process goes from one isotherm to another, but it goes like this. So it doesn't, does it look like a straight line? Maybe I should emphasize that this is not a straight line more, because if this were a straight line, then this would not be. Okay, so maybe let's just put it over here so that it's very clearly, there we go, very clearly not a straight line going up. So you can either go in this direction or this direction. And what makes adiabats, what represents adiabats, like what makes them special or whatever you want to call it, is that Q is equal to 0. So every single time in Physics 7A where we've had like an insulated container or like insulated from the outside, the word insulated basically means that Q is equal to 0. And so this is nothing new. In fact, we've been doing it more often than, you know, non-insulated, in my opinion. But so this is basically what it means. It means adiabatic process Q is equal to 0. So let's just go ahead and see what that means. So your work, again, can simplify. If you actually want to use this equation, you would have to actually do the integral, because otherwise there is no, you know, this thing is not like a rectangle or a triangle or something. It's like an actual curve that you would have to integrate. This is the area under the curve right here. And okay, but what does simplify? So Q is equal to 0. So that's, you know, your first simplification. And that's it, basically. So this is why I don't really like adiabats so much. Q is equal to 0, everything else not 0. Your delta P is not equal to 0 because you're going from some final, from some initial to some final. Delta V is not equal to 0 because, again, volume is either going up or down. Your work is not equal to 0 because even though Q is equal to 0, your temperature actually changed. The temperature is not equal to 0. The change in temperature is not equal to 0, I'm sorry, because you're going from one isotherm to another isotherm. So this is not equal to 0. Because this is not equal to 0, then change in thermal energy is not equal to 0, which means that change in internal energy is not equal to 0, which means that work is not equal to 0. So basically, with adiabats, in adiabatic processes, nothing really simplifies except for the fact that Q is equal to 0. So this is a process, this is a type of process in which you have to be extra clever and really make use of those equations that you have to solve your problems. In this case, it's just W because Q is equal to 0. You also get to use your thermal equation. and your last resource, which is actually doing the integral to solve problems. So this is basically the recap of your thermocycles. This is why we have, what we have is some sort of universal equations over here on the top. Then we decompose our processes into 4 different types of processes. And basically, depending on the process, your universal equations are going to simplify differently. And that defines what you can and what you cannot do with your equations. So now we're going to go ahead and solve several practice problems. I picked up a number of them. So if you guys found this little review helpful before doing some practice problems, again, I'm toying with the idea of going back to 7B and doing a bunch of these. If you thought they were useful, please make sure to leave a like, and that will basically let me know that yes, this is something that students are finding actually helpful. Otherwise, I'll just assume that this is redundant with lectures, so it's not really necessary. And we'll see where this takes us. So I'll see you guys on the next video. Have a great day. Bye.